Thank you. Okay, let me first take the opportunity to thank the organizers for this workshop. I really appreciate attending Frida. I think it's my second Frida, and I really like the discussions we have and the interesting talks, so thanks. Okay, so yes, I'll be talking about this very long title of parameterized verification of a particular type of distributed algorithms, so namely asynchronous run-based distributed algorithms. We'll see more what I mean with this, and we reduce this parameterized verification to a model checker, symbolic model checker, which is called NuXmv. So my background is in model checking, informal methods, and I know little about distributed algorithms, so please forgive me if I say something wrong, and I guess that's also the aim of this workshop, to get feedback from the other community.
Exactly.
Okay, so this is the way I see fault-tolerant distributed algorithms. So you have a number of participants, and say you have n of them, so n is a parameter, we don't know in advance which value it will be, and f of them are faulty. They could be faulty because they can crash, or maybe they are more malicious and they could have Byzantine failures. And f is not known, but what is often known is t, which is an upper bound on f. Okay, and t and n are linked via what is called a resilience condition. For instance, that there are no more than, okay, 2t is smaller than n, so no more than half of the processes are faulty. Okay, and more specifically, we'll be focusing on asynchronous run-based fault-tolerant distributed algorithms. So let me explain on this dummy example what I mean here, what is the kind of distributed algorithms I consider. So these can be, for instance, consensus or leader election protocols. We assume that processes communicate by asynchronous broadcasts, so they send message to all the other processes. And we assume that the behavior of each process is dictated by rules that are guarded by constraints, and those constraints are threshold guards on the number of received messages. So we'll see this in the example in a second. Okay, there are only finitely many local variables, and it is round-based, so it is structured in rounds. And all the rounds are identical up to the round index. The round index is used to tag messages, so when I get a message, I know from which round it was sent, and also from which sender. And there are some more assumptions. So we assume that the flow within a round is acyclic. We'll see this later, I guess. And something particular here is that the round increments are not limited to just +1. We can have increments as here of 2 or more. So jump to a round number which is not just the next one. So let's look at this dummy example. So it's just made up to illustrate all the features we can have. So it's a fake consensus algorithm where this represents the pseudocode of what each process executes. So in the first line, the process receives as input value either 0 or 1. Then initially it has a round index of 1, and it will go through the rounds in a while loop as follows. So first thing it does is broadcasting its local value, tagged with the round number. Okay, then it waits for a number of messages. So remember that there could be at most t faulty processes, so it cannot wait for n messages, it can only wait for n minus t messages of that particular round, tagged with the same round. And depending on how many messages of every type it received, it will do different things. So for instance, if it receives a large majority of messages with a common value w, then it will decide that value and finish. Okay? If it's not the case, and if it receives a smaller, if I'm not mistaken, smaller fraction of messages with value, say, 0 of that round, then it sets its local value to 0 and proceeds to, not the next round, but 2 rounds ahead. And the last case is if it receives yet a smaller number of messages with value 1, then it sets its own value to 1 and proceeds to the next round. So again, it's not an example from the literature. What I wanted to illustrate is the fact that one can jump to further rounds, not only the next round. This can be useful in some protocols, for instance, in Raft, leader election protocol. An important feature is that communication is broadcast to everyone. And and then here in that particular case, there's a single there are 2 local variables, the value v and the round number. Okay.
So broadcast. So maybe it's the same thing, maybe not. Like broadcast here means like unreliable, as in like if I am malicious, I can send 5 to him and 10 to him.
Correct. Yeah.
And was there a different question?
So here you're waiting for messages of the current round, of round R. Does it make sense to wait for messages of a different round?
What I mean with this, so I'm not sure I will answer your question, but what I mean with this is that in those counts here, I only consider messages tagged with R. Of course, I also stack or store messages from other rounds.
Right, but you would never have something different from R in your wait instruction, I suppose.
Yes.
Yeah. So.
Yeah. So it's somehow communication
closed. Kind of redundant, but yeah.
Sorry.
It's kind of redundant because exactly you assume that you have a communication closed.
Yeah. Yeah.
So maybe I wasn't listening. What were your assumptions? So you assume Byzantine failures, and you assume that n is large. What ratio of correct processes you assume n is larger than something?
Yeah. So I don't know. I mean, it could be from my perspective. It could be maybe 5T or anything. I mean, I'm not claiming that this is a correct algorithm, that it achieves consensus. That's not my point. Maybe that was an error, but I wanted to have a toy example that illustrates all the features we can have. But it's not I don't claim it is achieving consensus. Does it answer your question? Yes. And then there's a resilience condition. So say, for instance, 5T smaller than n, or maybe 2T or whatever. But my purpose is to say, if you give me such an algorithm with a resilience condition, how can I check that it fulfills correctness properties that are expected for a consensus algorithm? Does it make sense? Or does it answer your question?
I guess what I want to touch on what Stefan was asking is this: if there are like a communication pattern that goes across rounds, so you already have a little bit of not so well behaved behavior because you skip rounds.
Yeah.
So that's a bit more than simple communication close. Still, you don't, like if a message from an earlier round arrives, you ignore it.
And you wait for messages.
No longer test for a bound. Yeah. Sorry.
And also, like on the same page, you can have somebody at round 1 and 10 people are already at round 15.
Yes.
And they send their message. This guy at round 1 receives it and stores it. And when he gets to round 10, he on the line wait for n-t at round 10. He has them, although he received them when he was only at round 1.
Yeah.
So it's a lot of like subtlety in how these protocols are usually written down in human language.
Yes.
I do see a small problem. Like, what if
we are trying to break an English protocol.
If some nodes skip around, like you do the case R plus 2, then wouldn't other nodes that only skip one round not receive n-t messages?
Again, I don't claim that this works.
Okay. No, then it's fine. Yeah.
Okay, what I can say is that there are protocols where processes do skip rounds, and possibly here the bound is different, and also those thresholds here are different, and they don't achieve. So again, I don't claim that this is a consensus protocol that achieves it, but yeah.
Well, I'm claiming it's not even terminating ever, but
Yeah.
You could imagine that there's there's an else R is incremented, right? And then it would just catch up or race ahead or whatever.
no, it waits. It never increases R until it gets n minus t messages. And if one of the honest nodes never gets to that round R because one of the nodes gets to R plus 2 and all t faulty nodes,
If you
whatever.
prefer,
Yeah.
maybe we can remove this one and say that in all the cases you just... Okay, you claim, I mean, your point is about this.
Yes, yeah.
I understand.
And the point was just
I
about
understand.
And maybe like, okay, so we all agree this is not the correct protocol. And this will be the point to check it. But on the assumption side, because this is what you actually want to get to, a cyclic control flow is defined in this like compiler language of like, you know, what kind of jumps you can have with ifs and else's, you mean.
So I'll get to,
By
I'll get to
acyclic.
that, but to represent such pseudocode, I'll get to that in a minute, we'll use some graphs or small automata, and what we will require is some cyclic behavior in that automaton. But I'll get to that
Oh,
later.
that's good, that's good.
So, oh, yes. More questions. Yes, yes.
Again, in one round, a process can only broadcast once.
It could be, I mean, if there are different, say, local values, and so it could be, no, there could be several phases where it first broadcasts, I don't know, proposal, and then something else. And
If you have a bound of the faulty ones, you don't know how many essentially can send in a round.
I mean, it could be that, I mean, you could send a first message tagged with round number and also, I don't know, a tag that says this is the first broadcast of this round, and then a second broadcast of a different value. But you don't assume that a process will twice broadcast this. Okay? Okay, so sorry. Giuliano?
My question was about rounds being identical. What do you mean by that? I'm not
Okay,
allowed
what
to
I
have a
mean-
round in the if condition, for example? Or
What I mean is that up to R, you just repeat a while loop. Does it make sense? I mean, just R changes in the
but
description.
I'm allowed to say if a round is odd, do this, and it's even. If it's even, do
This you
that.
could unfold, so it would be fine.
Yeah.
Even odd. More complex things, I don't know, but I don't want the pseudocode to depend on R. Does it make sense? Basically, I want things that repeat, and the only change is the round index. Okay, so sorry if this example was confusing. Okay, again, my purpose was to say we consider what we call round-based fault-tolerant distributed algorithms with threshold guards. Important ingredients are that processes communicate via broadcasts, and there are only finitely many local variables to the processes, and yeah, that's about it. Okay. Okay, so let me now see what has been proposed in the literature for such for the verification of such algorithms. So, to the best of my knowledge, there are no fully automated techniques, and so most of them, most of the existing approaches are in some sense human guided. So there are many works in using interactive theorem provers where the users need to formalize the protocol into, for instance, TLA plus or ROC or another interactive theorem prover, and write the proofs that indeed they verify the base properties consensus algorithms should satisfy, for instance. So here I cite a number of works in that direction. This is very interesting, but it leaves high burden to the user who needs to write the formalization of the specification of the protocol and also write the proofs and interact with the theorem prover. And this really required some expertise in theorem proving. And in another work there, so again here the related work is focused to round-based distributed algorithms. One way to do so is also, can be to restrict the interleaving, restrict the schedulers, and reduce to existing tools. So for instance, ByMC, Byzantine Model Checker, is a model checker that can work for not round-based distributed algorithm, threshold-based. And what we managed to do is for a class of round-based distributed algorithm write invariant that reduce the verification to a single round specification and use that model checker by MC. And another way to do is to fix the number of processes. So say, for instance, you have 17 processes and use standard, or rather not standard, but use some other model checking techniques. So for instance, in this work, there are some reduction theorems to reduce to finite instances and then discard the, and use the TLC model checker to prove correctness. Or some people have encoded paxos for a fixed number of processes and fixed number of rounds in spin. Or there's also some work on some consensus algorithms. Sorry, I forgot which one. Okay, so I tried to somehow list into those three categories existing work on verification of round-based distributed algorithms. And this one is limited because it only proves correctness for a fixed number of processes, and the others really require some human engineering. So we'd like to somehow relax this, and this is why we propose another approach. Okay, so what are the challenges when one wants to verify run-based distributed algorithms? Well, there are somewhat two sources of infinity. One of them is the number of processes, which is a parameter, and it's not bounded, not known a priori. And the other dimension is the number of rounds, which typically depends on the number of processes, or is infinite, or is not bounded. And so we need to, if we want to apply model checking techniques, someone need to address those two sources of infinity. And another challenge is that because we have asynchronous communications, as pointed out in a previous question, it could be that one process is in round 15, another in round 1, and so the drift, so the distance in rounds between two processes, is also unbounded. Okay, so this is something that makes encoding into standard model checking programs difficult. So in the previous approach, what we proposed was to consider a restricted form of round-based distributed algorithms, RDAs. And for this restricted class, what we managed to do was to perform an abstraction that which is sound and complete, and transform it into a system with a finite-state system, but with infinitely many counters. And those counters can have unbounded values. And then on this system, what we did was to perform a CGAR, so counterexample guided abstraction refinement loop, which was customized to the object we had here, to try and verify the system we started with. So this approach, if you're not familiar with, CGAR, counterexample guided abstraction refinement, is not complete. So if you prove correctness for this, then you're done. But if you find a counterexample, maybe you can refine your abstraction and run again the check. But sometimes it's inconclusive. Okay? This is what we proposed in a previous work. And today I want to talk about a more recent work where we extend the class of algorithms we can deal with. Then we provide a series of sound and complete reductions to a finite counter system. So a system with only finitely many counters, whereas here we had infinitely many. And then we don't implement our own verification technique. What we do is just delegate the check to existing model checkers. And in particular, we reused, or we use NuXmv, which is a symbolic model checker, which has many verification techniques that can be used, verification engines, so IC3, bounded model checking, interpolation. And our hope doing so is to benefit from the many years of development of NuXmv or existing model checker, whereas in this particular approach it was our own prototype implementation and maybe not optimal. Okay, so in my view what we propose now has two benefits over the previous approach. The first one is that we generalize the class of distributed algorithms we can handle, and the second one is that we reuse some mature model checkers. Okay. Okay, so let me outline what I want to cover in the rest of the talk. So in the first section I want to tell a bit more about how we will model round-based distributed algorithms. So to do so we will use process templates, and we will express the properties we want to check in a new logic that we called history state count logic. Then I will just give an idea of the reduction steps we perform in section 2, and in the last section just one or two slides to say how we evaluated our methodology on experiments. Okay, so I'm again back with my dummy example, which is not achieving consensus. And I'll try to explain on this one how we model it. So in the model checking community, or at least in my restricted class of restricted community, we like to use automata to represent things. So this is an automaton that represents the behavior of a single process. So it can start, it has four possible locations, v0, v1, representing the value of internal variable v, and d0, d1, representing that the process decided 0 or decided 1. Okay? So this automaton comes with a set of parameters. In our case, we have n, the number of processes, so n copies of this, and t, the number of faulty processes. Sorry, an upper bound on the number of faulty processes. A resilience condition, so for instance, n greater than 2t, and a set of messages, and we'll see how they are used. Okay, and now I'd like to explain how we come from this to this, and this construction is by hand. We did not automate this. So on each edge, there's a guard and a round update. So I'll tell them here, but on the drawing I depicted the edges carry the guard, and I will explain how the form of the edges represent the update. And maybe before that, each location, so each local state is associated with or generates a broadcast. Oh, sorry, this should be V's. So V0, in V0, the message that is broadcast is M0, in V1 it is M1, and we assume that in the decision state they don't broadcast anymore. Okay, and maybe let me go to what are the conditions for the transition to fire. So for instance, when one goes from V0 to D0, this happens when the first condition is met. So this condition that we received, so the quorum condition expresses that we received sufficiently many messages, greater than n minus t, and then we received at least that many messages of type 0, then when local value is 0 or when local value is 1, we will go to decision state with 0. Does it make sense? So this G1 reflects the first case in that disjunction. Okay, now G prime 1 is similar, but the majority value is 1. And then the other two are for the two next cases. And what I use in this drawing is that a plain arrow represents no round increment, so you stay in the same round. A dashed arrow is increment of 1 and dotted arrow increment of 2. Okay, so r plus 2 or r plus 1. What did I not explain?
And the automaton is deterministic implicitly because it comes from code. As
Well,
it will always be a determinant. Like you will never be in a state where two guards can fire.
It could happen. Here it happens that on the left-hand side it's deterministic because there's a else if each time. But you could imagine overlapping guards and then it would overlap and that's not a problem.
I mean, technically, I see what you mean, but technically in code, there is always kind of a deterministic way the compiler resolves it. Like we kind of almost never have this kind of compilers that choose at random which guard to fire.
Or choose non-deterministically. You might have...
Yeah, like you have it in theoretical models, but almost never in actual code. But yeah, I see what you mean.
Okay, so this is what we call a process template. It also comes with the parameters and the resilience condition and this graph where you're given the guards, the constraints, and the updates on the round. So how many... you could have local updates. So for instance, you can move from value 0 to value 1 and then jump for two rounds ahead. Yeah.
So these are only the correct processes, but now you have different failure models, right?
Yeah. So for crash faults, you need not represent them. And for Byzantine fault, what we do is to encode, so add a special location where they can broadcast anything. So indeed, this is the behavior of a correct process. Okay. And, okay, maybe it should go a bit faster, but okay, maybe important thing is that what we want to define is what we call a parameterized semantics. So we want to collect all possible behaviors for all possible valuations of the parameters. So we want to consider the case where there are 100 processes and 17 processes and so on, etc., all together. So this is what we do here ultimately. We collect over all possible valuations that satisfy the resilience condition, these systems. And now what is a fixed instance semantic? So if I fix n and t, how do I obtain the behavior? Well, it's a transition system in which the configurations, maybe that's the important thing one should recall. So what do they store? For each process, they store its current location, its current round index, but also everything it has received so far, every message it has received so far. And those messages can come from further rounds or previous rounds. Okay, and there's also a network state that stores everything that has been sent ever. Okay? And intuitively, in an update, in a move, in a transition, what will happen is that a process can receive a new message, and doing so it will compare its... I mean, if there is a message in the network state that it has not received yet, it can receive it and add it to its multi-set of received messages, or it can move in the automaton, in the process template, according to a rule, if the rule is enabled by the guard. Okay? So there are only two kinds of actions, either delivering a message to a process, so a process receiving a message, or a process making a step. Okay. So these semantics can be seen as a transition system with infinitely many finite valued variables. And those finite valued variables, there's one for each round and each location. Okay, and you somehow count how many processes are in each round and location. And they are finite valued because we fixed the valuation. Okay? So we fixed the number of processes and n. Okay? But what is more interesting to us is this parameterized semantics that we want to check. So for all parameter valuations that satisfy the resilience condition, we would like to check that the property, correctness property holds. Okay. Okay, so let me now explain how we express the properties we want to we want to check. So we came up with this, what we call history state count logic. So it has two types of atoms. So round local atoms, so those alpha R, where we ask that a linear combination of the counters that count the number of process visits to location L in round R is below a certain term, a linear term also with variables n and t. So this is a round local atom, and it is used in a formula saying it will constrain all rounds. We will see example in a minute. I think it will become, I hope it will become clearer. And then the second type of atom is cumulative atoms, where you can sum these similar constraints over all rounds. Okay, let me explain how to express basic properties in this logic. So for instance, if you want to express agreement, then you will say that for all rounds, the number of processes that decided 0 at round R is smaller than 0, so is 0, or the number of processes that decided 1 at round R is smaller or equal to 0. Okay, so it cannot be that those two counters are positive at the same time. Does it make sense? So sorry, there's a typo here. It should be for all R. Now validity, if you want to express one validity. So if all processes start with initial value 1, then you want to ensure that for all round number, then the count of processes that decide 0 is smaller or equal to 0. Okay, I always write smaller or equal because it's in the syntax the way I can do, but of course you can read this as equal 0 in that particular case.
This assumption is outside the logic so far.
Yeah, so it's one validity, or the way I call it, like if they all start with this the equals 1, this is what happens. If they all start with 0, then replace 0 with 1 here. Yeah?
I was just saying it's not modeled in the logic, at least not at this stage yet.
Yes.
Right?
Yes. Well, you can encode, that's a good question, you can encode the initial configuration. You can encode the fact that they all start with value 1 before. It's not in the logic, it will be in the initial states for that particular case. Okay, termination says that okay, it's not the case. So sorry, here you go again. What does it say? Okay, I need to. So NC is the number of correct processes, and it's not the case that the number of processes that decided 0 or 1 at round R, it's never. Well, this number of this sum will eventually become equal to the number of correct processes. It's not always bounded away. I mean, it's not always smaller or equal number of correct processes minus 1.
This is a formula that's true when it has terminated, right?
This is true when it has terminated. If it terminates at round, say, 20, then this counter 20 plus this counter 20 will
at least NC. Yeah.
Will be at least NC, so at least NC processes will have terminated, decided. Okay, and this one is a variant of terminations that says, so assuming some, sorry, I forgot what it says exactly. If nobody decided at round R, no, sorry, that's not the way you should read it. Okay, sorry, I won't explain it now, but okay. And the last thing is leader uniqueness, where we ask that there is at most one leader in round R. Yes?
So this is a very classical logic, right? Like you can use existential for all and all that, like usual.
Yes. The difference with, I mean, the particularity I would say in that logic is those counters, specific counters, and the quantifiers that, I mean, quantifiers can be found in other logics, this area. Yeah. But the important thing to remember is that there are two kinds of atoms, I would say. So local atoms, and you want to check them for every round, and cumulative atoms, where you look at the effect over all the rounds.
This is a logic that you evaluate over runs.
Exactly.
Right.
Exactly. Okay, and maybe I didn't check what I'm...
Previous talk finished early, so you have a little more time. I think, technically you probably still have 10 minutes. Yeah.
So maybe I still have 10 minutes? Or?
Technically, yes, but
okay.
if according to the schedule, you can go 20 more.
Okay, no, but I will spare you this. So let me go to the second section, say, of this rest of talk, which was what reductions we perform. So we have this, let me go back 2 slides. We have this semantics, which is parameterized infinity in 2 dimensions. And, okay, what do we do to make it, to be able to feed it to a symbolic model checker? So the first thing can be found in other works. It's similar in spirit, for instance, to that paper by Stolkowska, Konov, Wieder, and Zuleger. It's the received message abstraction. So when you start one starts with a transition system in which the configuration stores every multiset of received messages for every process. Now an observation is that the only information needed, or most often the only information needed, is what are the messages that have been sent, and from this you can recover what transition you can fire. So that's what we write here. We only keep sent messages in the network state. We forget about received messages in the local state of the processes. And this is always sound. It's always a sound abstraction, and it's complete for what these co-authors have called common templates. And this is the link with the a cyclic flow, that I mentioned earlier. So within a round, if you can find 2 transitions, one appearing after another, then the guards somehow are monotonous. So it cannot be that you first check that M0 is greater than n/2, and then a constraint that is implied by this one, a small coarser constraint. So you will always, you will only be able to tighten the constraints. You cannot enlarge them within a round. So if you make this assumption on the process templates, then this abstraction is also complete. Okay, the second step is to say, at least in the pseudocode I showed, the process IDs, the process identifiers, they were not relevant. This is because the decisions processes make are only threshold based. They're only based on how many messages of a given type they received, not on who sent those messages, who typed those messages. So if the process IDs are irrelevant, the only important information is the number of processes in each location and each round. So this is a classical abstraction called the counting abstraction. It's quite classical in parameterized verification when you consider systems that are composed of anonymous identical agents. And it dates back to this seminal paper of German and Sisler. Okay? The third step is maybe a bit different from an abstraction. It's a restriction somehow. So far you have many possible interleavings, and with, as I mentioned, unbounded drift between the processes, for instance. And here we use a reordering technique that relies on commutativity arguments that were identified in this paper. And we use those commutative arguments to reorder the execution into what we call the semi-synchronous execution. And what do we mean by semi-synchronous here? So we don't mean that all processes are always within the same round. What we mean is that if you look at the sequence of transitions that is taken, the sequence of target rounds, so remember that you can have jumps, so the sequence of target rounds of each transition is non-decreasing. So it cannot be that the first target round is, 3, and then later you have a transition that says, okay, move to round 2. Okay?
What do you mean by target round?
Because
Then,
you start from a... So a process starts from, say, LR, and then moves to L prime, R prime.
Yeah.
And this is what I call target round. And remember that...
For a transition.
Sorry?
For a transition.
For a transition. And if you consider an execution, which is a series of transitions, if you only look at the target rounds here, so R prime 1, R prime 2, and so on, this is non-decreasing. Remember that this can be maybe R plus 2 or R plus 3 or something like this.
This is almost like saying that the rounds are non-decreasing per process,
yeah, but
right?
not exactly. I mean, yeah, you're right, it's close, but it's not exactly the same. For instance, you could have, you start from round 1. Okay, let me write it this way, I don't know if it's readable, but 1, and then you move to round, again 2. Then, okay, I try to make up an example. I hope it will be relevant. Then you could have 2, 3, but maybe afterwards you can have 1, 3. And see, it wouldn't be... here you would have 1, 2, 1, but the important thing is that you have 2, 3, 3. Does it make sense? So the what's important is that the target round follows a non-decreasing sequence, but the source round need not be monotonous.
Because you still do transitions on rounds in the past or what?
Yes.
I'm a bit confused on that part, I guess, on the fact that there is a source.
Process, no?
Yeah, it could be different processes. Yes, yes. This is the whole execution involving different processes. So this could be P1, P4, P2.
Okay, so P4 with 2, 3 on top means P4 transitions from round 2 to round 3.
Exactly. Yeah.
Okay.
Sorry. Yeah.
Okay, so this is the assumption. Okay, no.
And then we only look at the second component. So we only want the target. So that's what I call target round.
Yeah.
To follow a non-decreasing sequence. But it could be that the source round somehow is not monotonous. I agree it's close from saying...
No, it is different. That's initially I thought you mean it for one process and then
no.
makes less sense.
So it's really for the whole sequence. And so what we show is that as far as our properties expressed in historic state count logic are concerned, one can always do this reordering and assume that executions are semi-synchronous in that sense. Okay, and the last step is the following. Once we have semi-synchronous executions, then the intuition is that the counters that no longer influence the future, they can be discarded. Okay, this is also, I think, is quite intuitive. And if B is a bound on the jump you can do between rounds, then you only need a window of size B+1 to store the relevant information. Okay, and then you can have a sliding window of width B+1, and this sliding window can be encoded with finitely many counters. Okay. So here we really rely on the assumption that in the process template there's a bound B on the jump you can perform. This is important because it's a limitation for some protocols we would like to encode. Okay, and for common templates, when we reuse the terminology introduced by Stolkowska and others, these 4 steps that we have, they are sound and complete for the properties we are interested in. Okay, so maybe let me...
This is the real deadline.
Oh, okay. I'm almost done, but sorry, let me go back one step. So now, I think what I promised was to move from this ad hoc logic, historic count logic, to a more standard logic, so LTL, that can be used in the model checkers. So we need 2 more transformation steps that I won't detail to be able to move from this view with the cumulative atoms and the local round atoms to a temporal version of the property. I won't detail this, but there are additional steps, and once we do this, then we can express all the properties we were interested in in LTL, so linear temporal logics, for people who know, with, well, all of them, most of them have a globally operator here, saying that it's always true that something holds. So for instance, leader uniqueness, you say that it's always true that there's a unique leader, at most one leader, sorry, per round. Okay, and with these many steps, what we achieved was to reduce parameterized verification of this class of logic on round-based distributed algorithm to LTL model checking over the system with finitely many counters. Okay, the value of the counters are unbounded, but there are only finitely many of them. And remember, the way we achieve finitely many counters is this sliding window. Okay, and so this is for parameterized verification. And now if you fix the parameter values, it's even better because we reduce to LTL, but over finite-state systems. Okay, and just before concluding, let me report on the experimental validation we performed. So we did a handful, I would say, of case studies to try and demonstrate the applicability of our approach. So what the user provides is an SMV file, so a file with input format for NuXmv, which is the counter system and the LTL property, which describes the specification and the properties. And then what we used was the IC3 engine of model checker NuXmv. And we managed to verify those three consensus algorithms. So all of them have a round increment of just 1. So for these ones, we do not exploit this feature that you can jump more than 1 round ahead. You can see the number of locations needed, number of rules, the resilience condition under which we proved the correctness. And then for each property, agreement, validity, termination, and restricted termination, we indicate the time to complete the verification, and also in brackets the regression depth needed for IC3 to do this. Okay, so in my opinion, it is quite fast. And remember that this proves, this shows correctness for the parameterized semantics. So you don't know how many processes there are. You just know that there are n, and at most a third of them are faulty, for instance. So to me, it is powerful. Okay, and the second, the last benchmark is on a leader election protocol. So it's a Raft leader election protocol. So here the bound is 2. So you can jump ahead of 2 rounds. Again, number of locations and rules. And we managed to prove leader uniqueness in less than 2 seconds. Just to exercise the approach, we also tested about some bug variants where we changed the resilience condition, or we changed some threshold guards just to check that we did not introduce errors in our methodology. And when we do so, when we look at bug variants, the tool detects it and provides counterexample. And we also did some verification of fixed parameter evaluation. So if you fix 17 processes, then what happens? Okay, so let me conclude. So the contribution I wanted to present today is another approach to verification of correctness properties for a particular type of distributed algorithms that are round-based and threshold-based also. So the guards are on a minimal number of received messages of a given type. What we did was first a theoretical, let's say, reduction, so a series of reduction to encode this problem into LTL verification on counter systems. And then what we did was to do some experiments with NuXmv, which is a symbolic model checker for such systems. So there are remaining challenges, and when I first started looking at model checking techniques for distributed algorithms, I wanted to well, my background was in probabilistic model checking, so I wanted really to address the aspect of randomized distributed algorithms and how to model and verify probabilistic behaviors. Well, we're not there yet, so this is still to be done. And okay, and we don't know yet how to deal with algorithms in which the number of locations per round grows with the round index, and we also don't know how to deal with algorithms where the round jump is not bounded. So here we always add a bound which allowed us to have a bounded window. Okay, thanks a lot for your attention.
Quick question before well, maybe the next speaker sets up.
Yeah, so very nice. So since you're using IC3, you could get an inductive invariant out of the verification, but of course only for your encoded version, right? So I wonder if that could be translated back into an invariant for the original algorithm.
That's a good question. So indeed, it's on our counter system encoding. Now, all the steps, they are rather, I would say direct, or I mean, maybe it's a good idea that maybe we can lift the invariant back to the algorithm. That's a very good idea, but we didn't do so far, yeah.
Questions? Yeah, so I was wondering, so apparently it's one of the, is it first works which allow to do automatic verification for the parameterized semantic? Or
this would be lying. And also, I mean, I claim it's more automated, but what the user does in our approach is to input to the model checker the counter system, which is not the pseudocode. It's far from the pseudocode and far from the first semantics we have. So there's already this translation, all those translation steps that are performed by hand before providing the tool, the counter system. And there are other approaches for parameterized verification around.
Maybe in some sense I can add something. Usually when we present distributed protocols like this, we like to say things like wait for n minus t, but in fact the exact logic is quite involved because you need to wait for previous rounds, you need to allow next rounds, you need to think about termination and all of these like weird things. So in reality, if you start from a language which is a specific and specifies all of this, if you ask the user to be that specific, then you can probably create tools that automatically translate to automata. It's just that if you have this like, you know, intuitive, fits on one slide approach, this will probably not translate because it's not explicit. But if you use a language that is expressive, like that actually can be used to implement it, then you probably can make that link. You can make a layer that translates automatically.
Yeah, ideally what I think that's a goal that I don't know most of us, but some of us try to achieve is to have a real interaction between the designer of the algorithm and the verification people. And if someone first enters, I mean, if there's some template on how the algorithm should look like, and then they enter a first algorithm, then they are provided a counterexample, and then they want to refine, and maybe they also have some suggestion on how to refine this guard and all. I mean, yeah, maybe this will somehow contributes to that direction, but okay, again, I'm not the only one contributing to it. Yeah. Yeah, I'm sorry.
I'm happy to chat about it for a lot more, so
yeah, sure.
do it later.
We're already 5 minutes over, so let's thank the speaker again.